So this would be 12x dx. All we have to do is punch in 12 times 30 and times 0.1. So that is 36. Measurement unit, please. Excellent. Now we want the relative error, which is dA over A, which is 12x dx divided by 6x squared and 2. So this is twice dx over x, 2.1 over 30, or 0.1 over 15. And that will also be the percent error. We move the decimal point to the right, to your left. I got 0.006666. This is 0.0066, and here I will have 0.6%. No measurement unit, because we divide centimeter squared by centimeter squared. Last topic of this chapter. Any questions on what we covered? We can work on more board problems. 3.11. And you can say more functions? Yes.
Can you move the
Hyperbolic functions. There are 6 hyperbolic functions. I'm only going to ask you to look at 3. They have inverse functions. I'm not going to ask you to look at any. And of course, derivatives of 12 more functions, 6 and 6. I'm only going to ask you for 3. And here they are. Hyperbolic sine. It's not a sine function. It's a hyperbolic sine. Hyperbolic cosine. And hyperbolic tangent. There are 6, of course, secant, cosecant, and secant, cotangent, cosecant, and secant, cosecant. I'm not going to ask you anything about the other 3. I'm not going to ask you about the inverse functions for these 3, for these 6. Just these 3. Okay, how they were determined. Again, they are not trig functions. Okay, how they were determined. Let's look at the first one. E to the x minus e to negative x divided by 2. It's a difference of exponential functions. The next one is the same but with plus. Bless you. And hyperbolic tangent, of course, is hyperbolic sine over hyperbolic cosine. Or e to the x minus e to negative x over e to the x plus e to negative x. Okay, the question obviously is legitimate. Why more functions? Why do we need these? Well, it turns out that when they tried to hang a pole, between 2 poles, hang a cable, they couldn't come up with a function that uses maybe a quadratic model, or an exponential model, or what else? A polynomial. They couldn't. So they found out that this situation follows something like cosine, hyperbolic cosine. That's how they came up with this function. Said, okay, well, we have to model this somehow so we can figure out what the distance should be so the cable hangs correctly. Also, the same thing with the ocean wave. They were trying to model this, and they couldn't find anything that worked perfectly. But they found this function when they put together 1/2 of e to the x plus 1/2 of e to negative x. And they say, oh, that's it. Now, I have not been to St. Louis, but this is famous. In St. Louis, you'll find this arch. Well, it's a hyperbolic function. That's how they build it, using a hyperbolic function. Okay? So what do we do with this? Well, again, I would like to work on some problems finding their derivatives, and I'll explain the derivatives in a minute. Very simple, very similar to the trig functions. They are not trig functions, however. So let's find the derivative of any of these, where I'm only interested in hyperbolic sine, cosine, and hyperbolic tangent. And I will list the derivatives for you. And you're going to say, oh, this is easy. Then also we can look at a situation as a word problem with a telephone line. And let's see what they are asking us to do. So would you like to pick or I pick? Yes, I'm sorry, forgive me, page 263. Sorry. Okay, so let's determine hyperbolic sine, just one, and I'll give you the other ones. Or if you prefer hyperbolic cosine, we can do hyperbolic cosine. Which of these two or three, doesn't matter, the third one too, which of these you would like to prove? Just one. Okay, perfect, thank you. Good, so all we have to do is put 1/2 outside, e to the x minus e to negative x prime, right? We always take the factor outside. If it's at the top or at the bottom, it doesn't matter. I take it outside. Good, so 1/2 e to the x prime is that lucky function, good, but e to negative x prime is a different story because this is not plain x. So it's minus e to negative x times the e, exactly, very good. So this is 1/2 e to the x plus e to negative x. So now let's go back to our list and say, oh, I know this is equal to, exactly, hyperbolic cosine. Exactly, pretty much what you expected. Although, remember, they're not trig functions. However, cosine, hyperbolic cosine prime, you would have expected it to be, although it's not a trig function, but you would have expected it to be, it's positive. Same idea. And of course, what would you expect hyperbolic tangent prime to be? And you will be correct. Secant squared, right? Hyperbolic secant squared. I should have put the 2 after h. Sorry about that. Yep, that's it. So now let's practice. Please choose any problem you like with these three functions so we can illustrate their derivatives. So these are the only three that are your responsibility. If I put, which it's not going to be the case, I'm testing basic information. If I put any of that, any of the rest, I will give you the formula. You can look it up. You don't have to memorize more than this. So would you like to choose, or I will? Okay, let's look at 40 and 42. And you can choose the next. 40 and 42, 263. In 40, we have y equals, oh, I can't. It's a hyperbolic sine inverse. We can look it up at the formula if you want. But let's just say hyperbolic sine of tangent x. I don't want you to memorize more than what we have. That's good enough. So it's not really 40. I modified it. So we want to find y prime. Outer function, inner function. When I differentiate the hyperbolic sine, what do I get? Hyperbolic cosine of tangent x times the inner function prime, which is, that's it, done. Well done. Okay, let's look at That's it. Let's look at 35. I see it in red. Let's see why it's in red. 35. Y equals e raised to hyperbolic cosine of 3x. This completes our chapter 3. We do have time to start working on that handout. So, ready? Or we can just do more problems and I'll let you work on it over the weekend. It's up to you. And we do other problems. We don't have to start. That's fine. Perfect. So then y prime. Can anyone help with this? E to the hyperbolic cosine 3x. Good. Times hyperbolic sine of 3x times. Excellent. I wouldn't do anything to it. I will just rewrite it with 3 in front. 3e raised to hyperbolic cosine 3x times hyperbolic sine 3x. Do we understand this process or these steps? Everyone okay with this? Yes? Yes, Vanessa, please.
The 3, is that just from the cosine?
If this were just x, there would have not been a 3 here.
Yeah.
But this is not just x. So I have to differentiate the outer, then the next in line, and then the next in line. Better? Okay, so let's look at another. What about 32? It's a good refresher for the chain rule. G of x equals hyperbolic cosine of natural log x. We can modify it and put something else instead of plain x. So we can see 3 different functions. Would you like to do that?
Is that ln x?
Yes. Thank you. ln x. So g prime will be so first of all, no. We have to start from the outside. Hyperbolic sine of natural log x times 1 over x. So or you can write it like this as well. That's what you meant, right?
Yeah.
Perfect. Okay, so let's look at other problems. I'm looking now I'm on page 265, and we choose problems to review the entire chapter. So let's choose first to calculate or determine y prime from 1 through 50. So we start the review now. 1 through 50 on page 265. You choose. If not, I will. Yes. Okay, I will. Let's start with 28. Oh, and I forgot 42. I wrote 42 in there from the previous one, and I forgot. 42. Oh, I see why I forgot, because it's hyperbolic tangent inverse. We don't need extra formulas. We're fine with what we have. So y equals, in 28, cosine x raised to x. We're asked to find y prime. Any suggestions, any tips for us? How do we start?
Do the chain rule. Bring down the x.
Okay, so we want y prime x cosine x raised to exactly We cannot do that. Why? Because it's a function raised to a function. A function raised to a function does not have a formula. Then, what do we need to do? Excellent. So we have natural log y equals x times natural log of cosine x. Perfect. We applied natural log to both sides. We don't have a formula for this. We must apply log to both sides. Bless you. Any questions so far? Now we're ready to differentiate. Of course, implicitly, right? So the left-hand side, can anyone help with the left-hand side?
1 over y
Very good. 1 over y times
dx.
dy over dx. Now, we remember two things from last time, right? This is the notation for f prime of x. However, this piece and this piece mean something. If we separate them, they mean something. If we put them together, they mean f prime of x. Okay? So this is a differential of y, and this is a differential of x. But if we put them together, that ratio means f prime of x. Perfect. The right-hand side.
1 over cosine x.
Just ln cosine x.
Yes, if you use 1 and 2, this it will be ln. The order is the same. I mean, it doesn't matter. You can use that. Cosine x plus x 1 over cosine x times
Negative sign.
negative sine x, so you can put it at the top. So, any questions? Yes?
Can you review how you got that?
Yes. So this is function 1, and this is function 2.
Okay.
So 1 prime is, x prime is 1 times the second function plus this first function times the second prime. I differentiate natural log as 1 over cosine, but then I have to differentiate cosine, which is negative sine. So let's write it one more time for everyone to see. So the 1 over y dy over dx equals natural log of cosine x minus, and you can write if you'd like, x tangent x, just for simplicity. And then I multiply both sides by y because I need to get rid of it. But I will multiply. You can multiply by y and then replace. Would you like me to multiply by y first and then replace? Or you want me to multiply by the function? 1 step or 2 steps? 2 steps, very good. So then I will write dy over dx equals y, natural log of cosine x minus x tangent x. And then in the final step, I replace y by cosine x raised to the x, natural log cosine x minus x tangent x. Do we understand these 3 steps?
Did you just move the y to the other side?
No, I have to multiply. I cannot move because it's multiplied here. So in order to get rid of the denominator, I have to multiply both sides by y. I cannot break the product.
Okay.
If it were positive or negative, then I would have moved it. But it's a product. That's why I need to multiply. Better? Everyone? Yes? So, yes? Any questions? Do we remember this now? Okay. Let's do something else. What about finding the equation of the tangent line to a curve? Yes? Okay. Let's look at, let's say, 59 on the same page, 265. We are given y equals the square root of 1 plus 4 sine x, and the point is 0, 1. Find the equation of the tangent to the curve at a given point. Find the equation of the tangent to the curve at a given point. Any suggestions? Yes, so it's going to be y minus y1 equals the slope times x minus x1, where 0 and 1. Good?
Differentiate y.
Yes, I have to find the slope. in order to find the slope, I have to find y prime or dy over dx, whichever you prefer. So dy over dx equals. Can anyone help with differentiating this function? 1 over 2 the square root of 1 plus 4 sine x times 4 times
Cosine x.
cosine x. Very good. I'll simplify by 2. So I have 2 cosine x over the square root of 1 plus 4 sine x. So I'm after this. How do I determine it? I determine the function that gives the derivative, that gives the rate of change. In other words, its derivative. But how do I determine this? I plug in what? I plug in how much? 0, right? Good. I just couldn't hear. I'm sorry. Forgive me. So dy over dx, when x is 0, I get 2 cosine 0 over the square root of 1 plus 4 sine 0. Yes, Ricky, go ahead. Because I'm asked to find the slope of the tangent line at a particular point, and the point is given, 0, 1. Good. How much is sine 0?
0.
Perfect. Sine 0 is 0. How much is cosine 0?
1.
Good. So then the number is 2. So the slope of the tangent line is 2. Now we have all the pieces together, and we put them together. Y minus 1 equals 2 times x. X minus 0 is x. So then we get the equation of the tangent line as being 2x plus 1. Any questions on this problem? Yes, Regan, go ahead, please.
I was just confused on how we got 1 over 2, 1 plus 4 sine x.
The derivative? Okay, very good. So let's take a look. So we have, when we have the square root of a function prime, we have 1 over 2 the square root of the function times the function prime. So we wrote 1 over 2 the square root of the function times the inner function prime.
Okay.
Right? So it's 1 over 2 the square root times 4 times cosine. Better? Perfect. We tend to forget, so that's why I always take the time as much as we need to review. Can we continue? Is there any, oh yeah, let's go back and work on some related rates. Ready? Yes? Let's look at 97, same page. '97 on page 267. Let's read the problem. The volume of a cube is increasing at a rate of 10 cubic centimeters per minute. How fast is the surface area increasing? And remember, after the word when, you can forget it, right? You can forget the rest. Till the very end, when the length of an edge is 30. 97, page 267. The volume of a cube is increasing at a rate of 10 cubic centimeters per minute. How fast is the surface area increasing when the length of the edge of the edge is 30? So we are given 10 cubic centimeters per minute. We have to identify, we read the problem twice, we have to identify what is given, and we have to identify the question. So what is this? 10 cubic centimeters per minute. Very good, awesome. Good, and we are asked to find how fast is the surface area increasing when the length is 30. Yes, so dA, let's say, over dt. So this is what we're asked to determine. We are given the rate of change of volume with respect to time, but we are really asked to determine the rate of change of area with respect to time when blah, blah, blah. Yes, Ricky, go ahead. Good. Where is our starting point? Remember, the next step is I'm trying to find a relationship between these two. So I start with the
picture.
So this is the cube. I start with the volume. The volume of a cube, we just looked at it. It's x cubed. So what I'm asked to determine, first of all, what was the area? We used it a few minutes ago. 6x squared. So I'm asked to determine dA over dt because A is a function of time, V is a function of time. Well, what else is a function of time here? And x, of course. X is a function of time. Good. So when I determine dV over dt, how do I differentiate? Implicitly, because they are both functions of time. The left-hand side would be, indeed, dV over dt. What about the right-hand side? 3x squared. Ah, awesome. Good. Well done. Now I would like to do the same thing for this, and then we'll decide what to do next. Very good. Equals
12x
excellent.
times dx.
Right, because x is not a variable but a function. Awesome. So let's see what we have and let's see what we don't have. I'm after this. This is my variable. When? When x is 30 centimeters. This I have. This is a constant, but I don't have this. Is there a way of determining dx over dt? It's not given to us. Is there a way of determining dx over dt? Yes. From this equation, in which we have dv over dt as being 10. So 10 equals 3x squared times dx over dt. I want to solve for dx over dt so that I can put it in here. So please tell me what I should write. Solve that equation for dx over dt and tell me what you get. Indeed, 10 over 3x squared. That's all I need. And I will go back in here and replace dx over dt. So then dA over dt equals 12 times x times 10 over 3x squared. And you know me, I'm going to simplify first. X with x, 3, and get a 4. So then the top is 40 and the bottom is x. After simplification, I can plug in x equals 30. And what will I get? When x equals 30, I get 4/3. 4/3 what? Very good. Centimeter per minute, right? It's a rate of change. So centimeter squared is the area. Centimeter squared per minute. So the top comes from area and the bottom comes from time. Very good. Okay, let's look at another. Yes? 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 Yes, please.
Is the test.
So we'll talk about it. Just one moment. Do we have? Okay, we have 5 minutes. Let's talk about it then. Let me choose 3 problems for you. Yes,
I had a question on this one.
Yes, please.
To actually,
Yes?
Why did we differentiate V and A, like the volume and area equation?
Because I don't have anything about the volume. What I know is the rate of change. So volume would not help me. So that's why I wrote the volume formula, and then I differentiate because I needed to use dV over dt. Here I cannot use dV over dt.
And how did we know that dx over dt, or 10 equals 3x squared times dx over dt.
Because dv over dt was given to us, so I'm just replacing it here.
Okay.
I differentiate both sides to get dv over dt, and this is given to us, which is 10. Better? Okay, other questions about this before we continue? Okay, so let me assign a few problems. From page 260, yeah, I would like a linearization. So problem 1 on 255. Um, 19 and end 19. Okay, let's differentiate, let's say 31 and 33 on page 263. Okay, that's it, 4 problems. And